Uh, the next thing that we do in this topic is to determine the relationship between temperature and solubility. And we shall perform an experiment to do that. And so in this experiment we shall be investigating the relationship between temperature and the solubility of potassium nitrate. So what will we do? We will weigh accurately some masses of potassium nitrate, 2 grams, 4 grams, 6 grams, and 8 grams. Place them in separate test tubes that you will have labeled 1, 2, and 3. Then from a burette we will be adding a constant amount of water to each of the solid, and in this case we shall add 5 cubic centimeters of distilled water from a burette. And you need to be careful about how you use a burette to measure volumes, because I have seen students who just want to measure 5 and then they just from the burette they take a burette and fill it up to 45. Fill it up to 45, then they pour everything. Definitely you realize you don't have 5. You have unless you want to start from there and then you get to that point. You start from 45 and then you get to 50. Well, you can't do that. But if you was at 45 and then you run everything, then you definitely have more than 5. So I will therefore suggest that you fill the burette up to the mark, the 0 mark, and ensure this part of the burette is also full. Then you can be running from 0 to 5, then the next experiment from 5 to 10, and it will be very easy to do that. So whatever I said, you just get the 2 grams. Now in the first test tube, you add 5 cubic centimeters of water, and then you need to start that solution with a grass rod. Sometimes it may not dissolve completely because you have too much of the potassium nitrate, more than can dissolve at that particular temperature. So what we'll do is press that in a water bath. The content of the test tube, just press it in a water bath. Press that in a water bath, and as the temperature rises, it will the potassium nitrate is going to dissolve. Now you need to watch against heat overheating it, because the more you heat, the more you have to wait for it to crystallize. So then once the solid has dissolved, the solid in the test tube with the 5 cubic centimeters of water, it has dissolved, just remove it and then continue stirring with the thermometer until crystals just begin to form. And you'll be able to see that when the crystals just begin to form, record that temperature and proceed to the next one. Now if it is taking too long to cool, then you may have to maybe cool over cold water. Cool it using cold water, as we shall see in this particular experiment. So when that is done, I would expect us to fill this table. Now this part you're just filling the temperature at which the crystals just begin to form, of course in degrees Celsius. So you don't have to repeat the degrees Celsius. So just fill that part. Then this part we are filling the solubility, and solubility is supposed to be calculated. You're supposed to calculate solubility. What is solubility? The mass that dissolves in 100 grams of water. So we have 5 cubic centimeters of water. 5 cubic centimeters, that you will assume to be 5 grams. Of course it is 5 grams. The density is 1 gram per cubic centimeter. So 5 grams contains 2 grams of the solid for the first experiment. What about 100? And that gives me 40 grams per 100 grams of water. You can do the same with all the others. So like in this one, 5 grams contains 4. 5 grams contains 4. What about 100. Then you fill that table and you fill that, and then when you have done that, I'll expect us to draw a solubility curve. I'll expect us to draw a solubility curve. Note that this data is being obtained from the experiment. Or you fill it up, but this one is being calculated. Then you draw a solubility curve. What is a solubility curve? It is simply a plot of solubility versus the temperature. Temperature on the x-axis, the horizontal axis, the vertical axis. You put the solubility. So let's do the experiment and only come back to the discussion once you have drawn your solubility curve.
This lab will be finding the solubility curve of potassium nitrate in water. We're going to be working with potassium nitrate today, which is an ionic compound. It's a salt. And we're going to be seeing how soluble it is, how much of it can dissolve in water. So you see what it looks like here as a solid. First thing we're going to do is measure out a 2-gram sample of potassium nitrate. So we measure that out on our balance. And we'll take our 2-gram sample of potassium nitrate and put that in a test tube. And then we'll repeat that process with a 4-gram sample, a 6-gram sample, and an 8-gram sample, which I've already measured out. What we want to do now is dissolve them in water. So to each of those samples, we're going to measure out 5 milliliters of water. So we take a 5 milliliter sample of water, we'll measure it with our pipette, and we'll add 5 milliliters of water to each of the 4 test tubes. So we're trying to make solutions here with different concentrations. Concentration is the ratio between solute and solvent. So our solvent here is water, and we're having 5 milliliters of water in each of our solutions, and then we'll vary the amount of the solute, the salt, potassium nitrate. Okay, so we made up our 4 solutions with low concentration on up to a high concentration. If you look at the solutions right now, we can mix them around a little bit, and they don't dissolve all entirely right away. In order to make things dissolve faster, there's a couple things we can do. One thing we can do is stir it. That brings the solute particles in contact with the solvent more frequently and makes them dissolve faster. We can also change the surface area by making the particles smaller, or we can use heat. So when we heat things, generally at higher temperatures, they'll dissolve more quickly. So we're going to take the test tubes, I already have some set up from earlier, and put them into a hot water bath. And in the hot water bath, we're going to stir these solutions until the salts have completely dissolved. So this is what the salt crystals look like before they've been dissolved. You can see the little particles still in the solution. And then after we've heated them in a hot water bath for a little while, they'll look like this. So all the particles have dissolved, and you have a solution. In the solution, you cannot see any of the salt particles. Before they're entirely dissolved, you can see the salt crystals. So what we're going to do now is stir this and let it cool and see at what temperature will the crystals come back out of solution. To speed this up a little bit, we can use a cold water bath. So we have some ice here, and we'll dip this in and we'll stir it a bit, pull it out, we'll see if any salt crystals are forming. So far they have not. This particular solution has the lowest concentration of the 4 we're going to be testing today. This one has 2 grams of salt dissolved in 5 milliliters of water. So we're cooling it. We're down to about 40 degrees now. Still don't see any of the salt particles. So we'll cool it a bit more. Move it around in that solution. We want to, and here we have some salt particles starting to form now. You see it came out of solution. And we look at the temperature right now, and it's 25 degrees Celsius when those particles came back out of solution. So the saturation point for the solution with 2 grams of potassium nitrate in 5 milliliters of water was about 25 degrees Celsius. If we heated this back up, we could get the solutions to go back into solution. All right, next we'll do the one with 4 grams of salt. So this solution has 4 grams of salt. And we'll do the same thing here. We'll stir it and cool it. So far, no salt particles are visible. It's still a solution. And as we cool this down, we'll eventually reach the point where the crystals form. There it is. And that one occurred at 47 degrees Celsius. So at 47 degrees Celsius, the solution with 4 grams of salt in 5 milliliters of water started to crystallize and came out of solution. Okay, we have 2 more to go. We have the solution that contains 6 grams of salt dissolved in 5 milliliters of water. So we'll cool this one off. This one will go a little faster than the last 2 if the trend continues. So we're stirring this, and we already see some crystals forming there at the bottom. We just want to get it when the first crystals start to form, and that occurred at 66 degrees Celsius. So at 66 degrees, we started to get crystals out of the 6 grams of potassium nitrate solution. And moving on to our final and highest concentration. So this one contains 8 grams of potassium nitrate in 5 milliliters of water. And this one, we won't have to cool very much. We'll just dip it in the cold water kind of briefly. And already we see some crystals forming. And that occurred at 83 degrees Celsius. 83 degrees Celsius, and we got crystals of potassium nitrate forming in that solution.
Welcome back. I hope that is the type of data that you got. The solubility I've calculated, and this is the data that is obtained from the experiment. Now, where is your graph? That is my graph. That is my graph. What I call the solubility curve. So you know that at 20, now any point on the curve is a saturation point. That is a point at which crystals just begin to form. Why are crystals forming? Because it is saturated. So any point above it, it contains more. So like if at 20, I have a solubility of around 40, at 25 degrees Celsius, the solubility is 40. So any point above 40, it contains more than it can dissolve. So therefore, what will happen is that this one will crystallize until it gets to the 40. But any point below the curve is a point of unsaturation. You can add more. If it contains 20, at 25 you can add more. Now I want to say something about this curve again, that you know that I did not extrapolate. I did not extend from the 25, I did not extend from the 83. Why is that so? Because I am not sure. You can never be sure that this curve is going to, that this trend is going to be maintained. You can never be sure that that trend is going to be maintained. In fact, some students insist on bringing it to 0. That they insist that at 0, the solubility is going to be 0. That's not necessarily the case. So we don't have things like hanging graphs in chemistry. You are only, not even around, you are expected to get to the first plot and the last plot. Should you extend beyond that, that curve becomes wrong. It becomes wrong. So don't insist on extrapolation, on extending beyond your plot. Now, what other things do I need to say about the plot of about this graph? Now, the graph will be marked. There will be a mark for the axis. What about the axis? Did you draw the line? Did you draw the line? Did you draw those lines? I have not drawn them, so I may lose the upper mark for the axis. Note that I draw a line, I put an arrow, then I label the axis with the correct unit. That is mandatory for solubility. So this is solubility in grams per 100 grams of water, because solubility can be given in moles per liter. So if you don't put the unit, I cannot interpret your graph. You need to put the units. You need to put the units. And the temperature is in degrees Celsius. Again, the temperature is not in degrees. How can you measure temperatures in degrees? Did you use a protractor? Of course, you did not use a protractor. So the moment you put wrong units, you lose that half a mark. The other way you can lose that half mark is by inversion. Inversion. What is an inversion? You are told to draw the solubility on the vertical axis. Then you decide to put it on the horizontal axis. That is an inversion. It will be penalized. You'll be penalized for that. So you need to, okay, so the first thing you do when you get your graph paper is draw the lines, and then the arrows unravel, and the raveling is obtained right from the table. The next thing that we do with a graph is something about the scale. What about the scale? Is the scale consistent? Is the scale consistent? Like look at this. I decided to use 0, 0, but I could also have started from 40 here, 40, 50, because I don't need all this space. I don't need all this space. There's nothing I'm plotting in this space. So I could have started from 40, then to 50, to 60, to 70, and so on, like that. Then this side I could have started from 20. Some students will start from, they will put a big 0 there, then they will put their 40 there, a big 0 there, then they will put their 20 there, 30, 40, and so on. Have you seen what I've done? Put a big 0 there, then the 40, 50, 60, because I discovered I don't need anything between 0 and 40. So I put the 0 there, then the 40 there. Now, you know what will happen there? Is that now from here to here is 20, but from here to here is 10. So you have a wrong scale. You have a wrong scale. So if you do that, you can break that axis. Break the axis so that we know you have condensed the values in that region. Alternatively, if you don't write anything there, the examiner will give you the benefit of doubt. But that is only in chemistry. Understand, elsewhere you'll be penalized if you don't put the 0, 0. But in chemistry, you can ignore that. We'll give you the benefit of doubt. I will assume that here you started with 10 and here you started with 30. But that is so. But the moment you commit yourself to a big 0 there, then you must break that axis or have a cause. So that is what we talk of the consistency. Is your scale suitable? How does a scale become suitable? If your graph occupies 3/4 of the paper. Now, so I will look at my graph. Does it occupy 3/4 of the paper? Now, this is the first plot. I'm not interested in this region. I'll not count that as part of the area occupied by the curve. I'll start counting from the first plot, which is this one, and the last plot is that. So 1, 2, 3, 4, 5, 6 boxes out of 7, 8, 9. 6 out of 9, is that 3/4? If it is, I get so 6 over 9. 6 over 9. 3/4 of 9. 3 over 4 of 8 will be 6. If there were 8, I should have used 6. So this I've lost the scale mark. I did not use 3/4 of that. In the practical paper, we allow half, but in the theory paper, 3/4 of the paper must be used. If it's not, fine. There we are. We have lost half a mark for the scale. Now, is a scale accommodative? Now, I've seen some students who now, because they want to use the whole paper, they now talk of 0. What is that? Now they put the 40 there, then the 50, the 60, the 70, the 80, and now they need to have a 90. So what do? They add the paper. They don't even add it here. They add it on the last box here. They draw very carefully, and then they make their plot for corresponding to 90. That is not allowed. The graph is, the scale is not accommodative. It's not accommodative. The moment you encounter such, you have to redo your graph. You have to start from the beginning again. And you can decide on whether to sacrifice the scale mark. You can't decide to sacrifice the half a mark for the scale. But in most cases, the paper, I remember there was a time even in the KCSE where you either got the scale mark or the plotting mark. You had to either get, you had to sacrifice one for the other because the paper was not fitting. The paper wasn't fitting in a paper 3. I will get that. You can try and peruse through your KCSE papers and you'll see that actually happens. So you just your discretion, you can choose what to do. Now what else about that graph? The other point is a plotting. So it is better to use crosses rather than dots. Why do I say that? Because dots tend to disappear when you draw the line or the curve. They tend not to be visible. And if the point is not visible, then it's not there. You simply you copy it from a neighbor. You just put the line and then you traced from a neighbor. So that's how you take. If the plots are not there, then you do not plot your graph. So the plot must remain visible. For that reason, it's better to use the crosses. Now, the other thing is that do not round off if your scale allows. You must plot as accurately as your scale allows. Now, for example, I'm trying to plot 83. Somebody decide now I cannot go between the two small boxes. I cannot go between the two small boxes. So they decide to go to either 82 or 84. That plot is going to be wrong. It is wrong because my scale can allow me to plot 83. Why am I plotting 84? You lose the plotting mark if you round off, whereas your scale can round. Now, one thing that I also advise against is the use of 10 boxes to represent 3, 6, 7, 13, and such values where you cannot divide exactly. What is 10 divided by 3? So if I had say 0, 0, 30, okay, I put 0 and 30 there. So 10 boxes to represent that. So 10 divided by 30, what is that? Supposing I want to plot 31. Anything that is not on the bold line will be a wrong plot. Anything that is not on the bold line is going to be wrong. And I don't even need to struggle to see whether you have plotted it as accurately as possible. You definitely rounded off. So I will just mark it wrong. I'll look at your plot and see, is there any plot on the bold line? That is correct. If anything is not on the bold line, then it is wrong. And if you lose 2 plots, you get half a mark. If you lose more than 2, you get nothing. So everything you plot everything, or you lose 1, you get 1. If you lose 2, you get half a mark. If you lose more than that, so I look. The first thing I do is look at the easy places to penalize, and I cancel 3. If I lose 3, then I don't have to look at more of your plots, because it is difficult to mark, of course. You realize that. So you'll be making my life very nice if you use such skills. The life of the examiner becomes so nice, so nice. I wish 50 of you could do that. I will do the marking very fast because it's very difficult to look at that and then come back but if I can easily look at your wrong plots, hey, you'll become my friend. If you do that, I can also buy you what is your favorite lollipop? Right, I can do that. Please do that, and you'll get a lollipop, and then you continue to fail. Now, the next thing, so the solubility curves, there are several. The solubility curves can be all sort of curves. If you have been with me long enough, okay, you'll be with me for a long time, you'll discover that the graphs in thermochemistry must be straight lines, extrapolated. Graphs in reaction rate must be curves. They must be curves unless you are drawing the graph of 1 over t. There should be a straight line through the origin. But for solubility curves, they can be straight lines They can be smooth curves. I have all sort of curves here, like this curve. What does it tell you? As the temperature increases, what happens to the solubility? It is decreasing. An increase in temperature leads to a decrease in solubility. Now for this, an increase in temperature leads to an increase in solubility. And of course this one, it is almost constant. Almost constant. This is what happens actually to things like sodium chloride. It doesn't become very much soluble as you increase the temperature. It's negligible. Now, in fact, this is what you get for all gases. For all gases, the solubility of all gases decrease with an increase in temperature. You remember what you did in primary school? You got some water, you warmed it, you heated it. As you heated it, you saw bubbles. Why did you see bubbles? You saw bubbles because the water could no longer hold all the gas, all the air that was in it, so some of it had to escape. That is why you correct some gases over warm water, like nitrogen monoxide, like hydrogen sulfide, because the solubility of gases, the nitrogen monoxide may be highly soluble in cold water, but as the temperature increases, its solubility definitely decreases, so you can correct it over warm water. Now, allow me to mention something that we will come up with when we do reversible reaction. The reason why the solubility of gases decrease with an increase in temperature is because all gases dissolve exothermically. All gases dissolve exothermically. So, from the Richter-Terrier's principle, whatever that is, when stress is applied to a system in equilibrium, the system will respond so as to offset the effect of that stress. So if you increase temperature, you favor the process that leads to decrease in temperature. So a process that leads to decrease in temperature is endothermic. So an increase in temperature always favors endothermic processes. But we have just said that dissolving gases is always exothermic. So an increase in temperature will always favor the reverse process, less dissolving. So you discovered that for a substance whose solubility increases with an increase in temperature, it must be dissolving endothermically. It must be dissolving endothermically. You realize that the solubility of the enthalpy of solution of sodium chloride is just positive 1 kilojoules per mole. That is very small. That is why the solubility of sodium chloride may not be affected so much by an increase in temperature. Now we proceed to look at my graph, and we have looked at the graph. That is my solubility curve. So does the solubility depend on temperature? Yes, it does. So because at 40, that is the solubility. As the temperature increases, the solubility is increasing for the substance in question. And I think that was the solubility of sodium nitrate. So we can it was supposed to be potassium nitrate. So we can make that change. So the graph requires me to get the solubility at 55. The solubility at 55. How do I do that? Just get to 55, proceed to the curve, then you read the value corresponding to that. Please show. Please show. In the theory paper, if you don't show, you get nothing. You get nothing. Because you can always get that value by extrapolation. I don't know what extrapolation is. You say if the solubility at 40 is 25, or at 25 is 40, what about at 55? And you'll get a value. Did you use your graph? You did not use a graph. Or you must have read it from the table. So you've been told to determine from your graph. So if you don't show how you got the value from the graph, then you did not use your graph, you will not get that particular mark. So let's get those two values. I hope your graph is there. Read the solubility at 55 I need the solubility at 79. The next question you have been asked to do is to get the concentration of the saturated solution at 55. We did such a question, and there's no harm in redoing it. Just remind yourself how we did that. Now that you've worked out the solubility from the graph, then what about the concentration? Can that be done? So that is what I got. I will not give any allowance. 96 plus or minus 1. Okay, and 150 plus or minus 1. But it has to do with your graph. It must be from your graph. So I will look at your graph to award this mark. What is the concentration of the solution at 55? So I have the solubility there. Just converting that to moles. So 0.9505 moles. So what about the 1,000? Because these are the moles in a 100. In 100 cubic centimeters of water, I will assume that this mass occupies 0 volume. So I'll assume that to be in 100 cubic centimeters of water, not 100 cubic centimeters of solution. So I convert that to what about 1,000? We have done that. That can be done. The next set of questions: what mass of solid would be required to make 100 grams of saturated solution at 55? Yeah, those are questions you have come across. Again, you can still do that. 100 grams of. Have you underlined that word? Yeah, because you have to. If you don't, you will not get it right. So calculate the mass of water in 50 grams of saturated solution. You can pause and attempt those questions. Welcome back. That's the way I did it. Mass would be required to make 100 grams. So how did I get 196? I hope you have that. The solubility is 96 grams for 100 grams of water. So I have 196 grams of the solution containing 96 grams of the solid. What about 100 grams of solution? So that is what I get. You can apply a similar argument to the next question. Confirm that you got it correct. Next set of question: what mass of solid would crystallize if a saturated solution at 100 is cooled to 85? Is cooled to 85. Looking at the graph, a solution in 100 grams is cooled from 80. So if it is cooled from 80, then it must be containing around, or from 79, it must be containing around this much. But you have cooled it to this temperature. It can only hold this much. What does that mean? The difference must crystallize. At this temperature, it can hold 96, but it is containing 150, so it's above that. It's above the curve, so it cannot hold that much. It has to be, a bit of it you'll have to recrystallize. A bit of the difference must recrystallize. And how much will recrystallize? So if you have a 300 grams of water, it is holding 150, it can only hold 96, so 54 grams will have to recrystallize. What about the next question? Calculate the mass of potassium nitrate that would recrystallize if 100 grams of the solution is cooled from 79 to 55. 100 grams of the solution. Now, let me start here. Of course, at 79 it's 150, so I have 250 grams of the solution. 250 grams of the solution would give me 54 grams. Are we in agreement? If I start with this solution, that is 100 grams of water that is containing 150 grams, so that is 150 grams of solution. So 150 grams of this solution would give me 54 grams of that, sorry. It would give me 54 grams of that, sorry. But what about, so 250 grams of the solution would give me 54. What about 100 grams? And I think I get that to 21.5 grams of the solid would recrystallize. The alternative way of doing that would, now you realize that when I have 100 grams of the saturated solution, 100 grams of saturated solution, I cool that from 79 degrees Celsius to 55 degrees Celsius. Now, I start with 100 grams of the saturated solution. I will not end up with 100 grams of the saturated solution because some of the solid is going to crystallize. So the solution I have here will not be 100. So it would be wrong to say 100 grams of the saturated solution can hold. So if 250 can hold 150, so what about 100? I get the value there. Again, if at 55, if 196 can hold 96, what about 100? It would be wrong to do that. Why? Because the moment I get to 55, the mass of the solid is no longer 100. Some of it has crystallized. So that is the wrong approach. The correct approach would be, the correct alternative approach would be to get the amount of water, because the amount of water remains constant. So if how much water do I have in 100 grams of the solution at 79? So 250 is dissolved in 100 grams of water. So what about 100? And I can do that. Okay, I have 40 grams of water. Now, so 40 grams of water, and how many grams of the solid? So mass of the solid, it's 100 grams of the solution, so I have 60 grams of the solid. Now I cool that the same amount of water. The water remains constant, so I still have 40 grams of water. How much solid can it contain? If 100 grams of water can hold 96 grams of the solid, what about 40 grams of the water? Because cooling does not change the amount of water. So that is giving that 8.4 grams of the solid. So the 40 grams has 60, it should only hold 38. So the difference must crystallize. So 60 minus 38.4, and I think that should come to 21.6. Should come to the same thing. So note that is an alternative approach. That should give you the same answer. Let us look at the two questions. And you can take time, get the answers, discuss them with a friend, discuss them with your teacher, but arrive at the same answer. But now, finally, we look at the application of solubility and solubility curves. We can use solubility curves to separate salts that have different solubility, and that is actually what we did in the solvent process. So it is not that sodium hydrogen carbonate is insoluble. It is only that you have obtained too much sodium hydrogen carbonate. The amount of sodium hydrogen carbonate that is obtained during the process, especially when you cool, is higher than that can be dissolved. So it is not really a precipitation reaction. It is a recrystallization. It has the excess mass crystallized. So when you separate salts that have different solubilities, if you have different salts that have different solubility, you call that fractional crystallization. Just like we talked about fractional distillation, there will be crystallization, simple crystallization. You don't have to say simple, but you talked of simple distillation. But there can be crystallization. If I have some salty water, I allow it to cool, crystals will form. That is crystallization. But I have a mixture of sodium chloride and potassium nitrate. I want to separate them. Then I do a fractional crystallization. And this is a question you'll come across in papers. The table below gives the solubility of potassium nitrate and potassium sulfate. And there you are. And what is the question? Yeah. When aqueous mixture containing 60 grams of that and 7 grams of that in 10 grams of water at 80 was cooled to 0, some crystals were formed. That is, then you're asked to identify the crystals. Can you do that? If you can get back to the table and compare. It contains 60 grams and 17 grams, let's say in 100 grams of water at 80, 60 and 7. Get back to 0, and this one contains 80 grams, no, 60 grams of potassium nitrate and 7 grams, 60 grams of that, 60 grams of potassium, and then potassium sulfate is 7. And you have cooled, so it was at this point on 80 or whatever the value was, but you have cooled to 0, and you have 60 grams. You still have the 60 grams. If you have 60, it can hold 55. It has 60, but it can hold 55. So it has more than it can hold. Therefore, the excess you'll have to recrystallize. You have 7, it can hold 10. Therefore, it doesn't have enough. You must add more. So whatever will crystallize is potassium bromide. What do you call that process? Of course, that is fractional. The method used is fractional crystallization. Determine the mass of the crystals, you just subtract applications of the same. Maybe in Rick Magadi. Forgive my pronunciation, but I know how to write it. When you want to separate sodium chloride from trona, from sodium hydrogen carbonate sodium carbonate. Trona, of course, is a double salt. Sodium carbonate, sodium hydrogen carbonate. You want to separate these two, you use fractional crystallization, as opposed to crystallization alone is used in obtaining sugar. And I think even in Mombasa, in the Indian Ocean, when you get the common salt in the Indian Ocean, it is you don't do fractional crystallization. It is just crystallization. But with Rick Magandi, you have to separate the two. You have to separate the two salts, and that is it. So that is it about the effect of temperature on the solubility.